GM, everybody, happy Friday. Yasin here, and we're in for the last workshop of the week. We're having Simon Lau from Polyhedra coming in to talk about CUDA-accelerated GKR Prover. Again, so a few things to keep in mind. For those of you that did not see the announcement that we sent out earlier today, we are going to be moving in towards the building stage of the bootcamp, which is going to be starting on Monday. That means for the next 4 weeks, you will be able to engage with one of the 5 bounties, and you will be able to build and submit your project if you wanted to compete for the 50K bounty price associated with each of them. Hey, Simon.
Hey, Jansen.
Just a quick response to some of the questions. It's going to be yesterday's going to be only one talk. Simon's talk will be the last one for this week. For next week, we do not have any planned talks at the moment, but we are trying to organize several sessions which will cover all the bounties and provide some additional ideas and depth about the things that you can engage with, things you can build, and how to build the very best projects possible and win the prizes. Right, Simon, shall we get into it?
Yeah, sounds good. Cool. Hi, everyone. My name is Simon Lau. I'm a research engineer from Polyhedra Networks, and I'm mostly working on using the CUDA and the GPU to accelerate our expander provers. And today I'm going to show the fundamental knowledge that you require to use the expanders and how the GPU acceleration works. And I will give a simple example about the fundamental protocol, which is the sum checks. And on top of that, I will show how we actually build the entire expander provers. Just a reminder before I start the actual talks, if you have any questions, feel free to post in the question tab or just raise the question in the chat. I'm not able to see the chat tab, so please stop me, Jansen, if any audience asks any questions. Feel free to stop me. And the talks is going to be about 40 minutes, and I will left about 20 minutes Q&A sessions if you have some more questions. Yeah. So today content is basically the expander is built on our the paper from our one of our co-founder Tiancheng Xie, and his works from 2019's linear GKR is basically how we build our expanders. If you check the code, by the way, all of the codes are open source. If you check the codes, it's basically a very solid implementation of the linear GKR. And what I'm doing right now is that I move the code from a raster implementation to CUDA implementation so that it's being able to run on the GPU, and you have a lot of accelerations. And in order to do that, there are multiple ways to move to the GPU. You have PyTorch, you have tools like Triton, or you can write your CUDA. And if you're hardcore, you can just write your own PTX instructions. So there are many ways to do that. And we actually tried some of the ways and to see the trade-offs between. And, proving requires different curves, different fields, and you have different GPU and you have different CPUs. We are also doing some benchmarks on different machines to see the trade-offs. And I will show how exactly you can use the open source code to run the prover that on your own machine if you have a GPU. We have some performance benchmarks and bottlenecks analysis, and an end-to-end showcase to how to starting from the applications, and you go through our compiler. I believe some of you guys attend the front-end sessions that show you how to use the compiler and generate circuit, and then you can load the circuit to the backend prover, and the prover can either be run on the CPU or on GPU, and you will have different performance. So that's basically the outlines of today's talks. Now, in order to give you guys some backgrounds about the LIBRA, the linear time sum checks, I was starting from this equation. So this is basically the purpose of doing sum checks, which is a fundamental part of the expander workload, which is try to prove age. so h is equals to a sum, and this sum is a polynomial sums, and each of the variable is either 0 and 1. So you have number of log n variable, and you sum all of them together. And back to the Tyler 13 published in 2013, and there's a way to do that. So you basically initialize the tables and you sums all of them together, and the time complexity goes to ON. So I'm not going to dig too deep in this calculation. I just want to show you guys, like, there's a paper describing what is the sum checks, and we can actually doing that in the linear time. But if you use the old way, the way that proposed in Title 13 to do the lim check, to do the sum checks, and used it as a basic component of the GKR protocols, you are actually going to have a square and time complexity, which is not acceptable. Again, I'm not going to too deep in the equation, but this is how this is the problem that we are going to solve, and it's actually being solved in Libra. Am I having a laser cursor? Never mind. Yeah, so in the Libra papers, we have a linear time way to solve that. And the way to do that is that in order to, instead of calculating this equation, we break it into two phases. The first phase, you are summing up all of the variable first. So in the sum check, we have two variable, and you sum up one first and building a lookup table. So in order to better understand this, thinking about, you have 2n variable, and instead of doing all of the sum checks work for those 2n variable, we break it into two phases. So we process the first n, and then we process the second n. And by doing so, you basically have a way to lower the time complexity from n squared to n to 2n. And that basically make it to be linear. But in order to do that, you have to have a way to building a lookup table. It's like a cache. It's like a faster way that you can do the sum check for the first for the first n variable, and then you build another table, another like lookup table, so that you can process the second part faster. That's a very clever idea proposed by Tianchen in his paper back to 2019. And as I mentioned, we break it into two phases. So the second phase, you still need to initialize the lookup table and run the original algorithm from Title 13 again. So this is some complicated background, but the takeaway of this background introduction is basically direct the people who are interested into the actual theory behind to the right paper and to our own code. Okay, so to sum everything up, so this is like the computation that we are going to put on our GPU. So as I mentioned before, the purpose is just to proving that something is equals to a sum, which is sum checks, and we break it into two phases. Phase one, you do some initialization, run the original sum check, and then the step three, you initialize another lookup table, then you do the sum check again, and you return all of the result. So all of these results are executed on GPU, and in between, because this is like an iterative proof, so we have many things to prove sequentially, and every step requires a random challenge, and the random challenge is generated from Fisher-Shamir function, and that's also being done on the GPU. Sorry, this is a typo, on the GPU too. And yeah, so that's pretty much the entire walkthrough of the background knowledge that we are going to put on our prover. I want to pause for a while to see if there's any questions so far before I proceed to the actual implementation details. Jensen, is there any questions here?
Right, yes. So there is a single question. Are there some operations that can be done on the GPU?
Are there some operation that can be done on the GPU? Yes, but they are very minor operations. Most of them, you can think of the GPU is like 10,000 small CPU. Each CPU, each core, each CUDA core is fairly small, and the thing that they can do is limited, but it's basically Turing complete. So you can do everything you want. It's just slow. So we selectively pick some operations on to put onto the GPU and making sure it's not cost us so much performance loss. For example, like I mentioned in here, so between the phase 1 and phase 2, you will need to have some random challenge generated from a hash function. It's called Fisher-Shamir process. So the Fisher-Shamir process is basically requiring you to running a hash function. And the hash function is not very friendly on GPU. So originally we put on the CPU, but the amount of the work that you need to hash is fairly small. So even if you move to the GPU, it won't cost you a lot. So in order to answer the question, there is no function or operation that cannot be done on the GPU, but we move to the CPU on the purpose of performance. Well, the CPU is faster on some certain workload like hash function. Okay, I'm not seeing any other questions, so I'm going to proceed to the next part.
There was a follow-up by Nuh just now. What about operations that might be required to be done in a sequence?
Yes, and that is so Fisher-Shamir is exactly the one that, as you mentioned, done in sequence. You need to so in the context of the GKR proof, we have many layers, and between each layer or between each subject process, you will need to generate a random challenge by using the Fisher-Shamir, and that is like obviously a sequential operation, and you cannot parallel this because hash function it's kind of hard to parallel, but there's a way to parallel. But the main point of that is that the whole point is that you need to do this hash function one by one, and this is not what the GPU built for. So what we do is that we explicitly using just one single core from the GPU to do that hash function, and then the rest of the work is done on all of the core of the GPU. So that becomes the bottlenecks. And the reason why we want to put on the GPU is like simply because it's too small. Like you can transfer the data you want to hash to the CPU and do the hash on the CPU and then transfer back to the GPU. You can do that way, or you can just use the slow GPU core to do that hash function with single core. It's fairly slow, but you save the time to talk back and forth between the CPU and the GPU. And I will show you that it's just very short amount of the work, so you don't need to worry about that. And we starting from the CPU and then we move to GPU, we found that it's nothing, so we like just stick on the GPU. All right, so yeah, so the entire GKR process is basically, as I showed in the slides, it's like 10,000 feet view for the GKR process. And if we check the paper, the GKR proof is basically layer by layer from output layer to the input layer. And to give you guys some basic understanding of what GKR is, it's basically convert your computation, any computation like hash function, like KCAG, all of those functions that can be represented as a circuit. And the circuit is not like the electrical circuit we know. It's like an arithmetic circuit. And the arithmetic circuit is having two operations, addition and multiplication. And from the output layer, you have the result. And then you go layer by layer until to the input layer, you got the input of such computation. And what GKR does is it's first using the output of such computation, like the hash result of some hash function, and we commit it. and sorry, we commit the input, and we use that as an we use the output of such computation as the input to this proof process. And by layer, we got to the input layer, and at the input layer, we double check that if the result is equals to the input variable that we commit to the GKR. Again, this is a very complicated and comprehensive process, which is not the focus of this talk. The focus of this talk is mainly about the GPU. But the takeaway here is that the GKR process is layer by layer, is sequential. So this is something that you cannot do in parallel because every layer depends on the pre-layer's output. Every layer's input depends on the pre-layer's output. So at a time, on the GPU perspective, we are only processing one single layer at a time. But for sure, you can have multiple threads running on CPU that calling the GPU in parallel, so that that is another level of parallelism. So we can now zoom into the layer computation. So for each layer, if you recall what I showed in the previous slides, we actually break the entire layer computation into two phases, phase 1 and phase 2. If you remember, I will go back to here. Yeah. So phase 1, first we build some lookup table, we run the original sum check, and then we build another lookup table for the purpose of speed, and then we run the original sum check. And that exactly looks like this. So we build up some lookup table in order to accelerate the computation. We do the actual sum checks like folding. So I'm not going into too deep about what folding is. And then we prepare the lookup table for the second phase, and then we do the actual sum checks. And the output of this layer as the sum checks will be sent as the input to the second layer, and so on and so forth. So typically one arithmetic operation like KCAC, you have about 149 layers in total. So you can think that this procedure will be repeated 150 times. And at the very beginning, we're starting with a Triton-based implementation for proof of concepts, and we run this procedure for 64 times. It's like having a 64-layer arithmetic circuits, and each layer is having 28 variable, which making the workload size to be 2 to the power of 28. It's running on NVIDIA H100s, no pipelining, no field shamir. No field shamir means that the random challenge of this procedural is pre-prepared, like being generated on the CPU at a time. It's not being generated from the previous computation of the sum checks. And we are working on this procedural on the field of M31 extension 3, and it's being completed in 3 seconds and 49 microseconds for each round, for the total of 64 rounds. And we also implement something similar that on CUDA, and still there's no pipelining. No pipelining means that we are not running the entire sum checks in parallel. Like the first circuit is running on the second layer, and then the second circuit running on the first layer, and so on and so forth. So there's no overlapping between the layer. But it has the field shamir, meaning that for the entire arithmetic circuit, the random challenge is generated in the real time. It's not being defined before the GKR computation. And then it's also running on the M31. Still, we find that the speed is roughly the same. It's a little bit faster, but is roughly the same. And so then we decide to go for the native CUDA implementation. But Triton is good. Triton gives you a very easy to use interface to use something that you already written in Python, and then you directly call Triton, and then there's the compiler in between and give you some good performance. So it's basically remove all of the pain you need to pay for writing a native CUDA implementation. And so this is the code that we already open source. If you go to our GitHub repo, and if you go to the expander under the main branch, under sum check and CUDA, you will be able to see the actual implementation. And this is like an output of this standalone GKR one layer prover. And we also have a nice way to print out of the time breakdown for each of the procedural, so that you know where you should optimize for. We also support different fields, and there's a way that you can see a very, very verbose way, verbose time breakdown, and you know like which part of this computation you need to optimize. And also, for example, like the PCIe transfer time, and there's some time that's being spent there because not all of the computation is being done on the GPU. We tested basically on different kinds of the CPU and different kinds of the GPU. We'll try to include the 5090 officially released today to see how fast that our GPU prover can be. But this is the up-to-date data that we have for this benchmarking. Okay, and in order to do that, you will for sure having an NVIDIA GPU, and the version of your GCC need to be higher than 12.3. And the most important thing is that the CUDA compiler have to be higher than 12.5. And that is very important. And anything below 12.5 will fail. And the GPU memory requirements is obviously a very important parameter you need to be aware of. And after you run the compile command, it's just a make and make clean. And if we want to switch the fields, you can use this environment variable to switch which curve that we are, or which field that we are running the sum checks to on. And this is the command that you can select either you want to use the CPU or you want to use the GPU to do that. And if you want to see a very verbose time breakdown, you can add the -v to do that. Okay, so this I'm going to jump to the terminal to show how this tool works. And before that, I want to check if there's any other question. Yeah, M31 is refers to a Mersenne 31 prime number. That is true. And the extension 3 is that because the native Mersenne 31 only have 31-bit security, so it's not enough, and we extend it to B3 so that we have 93-bit security. It's kind of like extending a very narrow bit field element to a wide bit, but not too wide because we don't want to sacrifice too much computation resources. You can check there. This is like a typical way you extend some small field to or a wider field. Yeah, it's like an extension field. So you like GF2 extension 128. Yeah, like we can do extension 2, extension 3, extension 4. But extension 3 is, yes, so this is the question that we are aware of a long time ago, about 4 months ago. People are asking why you're using extension 3, not extension 4. It simply because it's enough. We did some computation based on the cost to break the extension 3, but we do support extension 4. It's like orthogonal to the actual expander implementation or sum checks. It's just the selection of the field. Which actually, so extension 3 actually give us a lot of troubles because, 3 is not a perfect number for memory alignment because M31 takes 4 bytes and extension 3, meaning that you have 4 bytes, which is 12 bytes. And a 12 byte is very unfriendly to memory arrangement because machine prefer something which is power of 2. So either 8 byte or 16 byte, 12 byte is a weird like arrangement in the memory, but it's saving you some computation. It's saving you about 25% of the computation, roughly. So, and it's the number of the security bit is enough to have the security. So that's why we chose the degree 3 extension. Yeah, thank you, Zhenfei. I think Zhenfei mentioned that we can support both degree 3 and 4. Yeah, that is correct. And degree 3 matches the security of a FIR, about 80-bit or 93-bit security. Okay, I will proceed to the next part, which is the hands-on tutorial. Yeah, so this is basically the expander repository, and yeah, so we just released the version 1.0.0 about 4 days ago. And after you clone this repository, you can go to the sum check and the CUDA. The name is the sum check, but it's actually a end-to-end GKR implementation. So it's actually proving a layer and also running a verifier. And yeah, so it's not just sum check. It's a complete version of the GKR Prover. And what I will do is first, obviously you need to, I make the same mistakes you do. So you need to load the CUDA. So this is my way to load the CUDA, and making sure that MVCC is under your path, and you make clean. So it's remove the binary, and you make it again. Yeah, you make, and that's it. And the way you need to do is just run the sum checks, and we choose the CPU, and we can do the 26 variable, which creating a problem of 2 to the power of 26, and you run it. So it's randomize the input and evaluating the output, and also commit the output. And it's starting to run the CPU prover. It's taking some time to prepare the data and run the actual sum checks. And then it's running the second phase, prepare and run the sum checks. So, and it's bring out some time breakdown. So this GKR, linear GKR, is spending about 6 seconds on the preparation of this lookup table, and the actual sum checks is fairly fast. It's about another 6 seconds. So it's 50-50. And in total, it's contributing about 12.17 seconds in total, and creating a 1.8 kilobyte proof. And we also have a very naive implementation of the verifier, and the verifier says it's passed, so it's a valid proof. And all of these are open source. So if you download the expander, you go to the sum check CUDA, you will be able to see all of the implementation. And this is the CPU prover. And am I on the same path? Yes. And if you run the GPU version, you simply just change it to GPU. And it's also doing the randomization, evaluating the output, and the commit. So this phase is fairly done on the CPU, and the GPU is relatively fast. So you can feel from the time it takes. So it's giving you about 4 times faster end-to-end speed up than the CPU. Again, this is something that we've been completed about 2 months ago, about 3 months ago, and this is not something up to date. And we are having a implementation of this end-to-end GKR prover, which is about 10 times faster than the CPU. So this is something like already open source, and you can give it a try if you have the GPU. And we move mostly everything to the GPU, so you can see each phase of this computation is slightly faster. Sometimes it's slower, but most of the time it's faster, and it's dramatic. It's super fast in terms of the sum check. So it's roughly, I guess it's 300 times faster in terms of the sum checks. And we basically spend our effort for the past 2 to 3 months to optimizing this part. And overall, it can be 10 times faster compared to a multi-threaded CPU. Yeah, I guess there will be no time to for the audience to try these tools in the real time, but this gives you a way to, if you are interested, you can look back into the recording and do what I did. So making sure that you have the CUDA compiler included, and making sure the version is higher than 12.5, then you can give it a try. You will at least have a 4 times faster GPU Prover from Expander's code. All right. Okay. Any questions so far before I can proceed to performance benchmarks and trade-offs? I'll wait.
A few, but Jennifer has been really active in chat and responding, so
okay,
been covered.
Okay, that's good. Yeah. So let me make it right. So so how fast it is? So we compare to the CPU, as you just saw. If we are looking at for the M31 extension, it just ran a 2 to the power of 26 here. It's roughly about 300 times faster for the sum checks part than the CPU, than the single-threaded CPU. So it's fairly fast. And the GPU is NVIDIA H100. So if you don't have that one, you have 4090, you have H100, or you have 3090, you will see about 300 times or 500 times faster proof time on GPU. So if you have the GPU, then you just run the GPU on Prover. That's the takeaway. And the maximum speed up for the sum check part you can reach is about 3,000 times faster to for a circuit set that is 2 to the power of 29, which is done on the H100. That's fairly fast. And we also try different CPU, different GPU, and different fields. So it all show the same curves. We are talking about at least 100 times faster for fields like M31. But of course, M31 is not secure enough. So if you are using the M31 extension 3, we are talking about multiple 100 times faster. And for the BN254, because it's like not very friendly to the CPU too, so the GPU can show the best speed up. It can reach about 1,000 times or even higher than that, like 3,000 times faster in terms of the sum checks. But that's not enough, because if we look back, there's not just sum checks. There are other computation, like how to prepare the lookup table and how to do the computation for the lookup table. Because the reason why the sum checks can be so fast is basically we are using the techniques from the paper of our co-founder. And in that paper, it's showing the techniques that you can, using the algorithm improvement, to speed up the computation of the sum checks. And that's why it can be so fast. And that's basically what we are doing for the past 2 to 3 months, which is improving the performance of this tools. And we are using different techniques. I'm not going to show like the exact code and how we actually run it in this. I will show a end-to-end run, but I'm not going to dip into too deep in the code. But this is some ideas that we actually used into our GPU Prover, the current version, not the 3 months ago version, which is pipelining. So as you can see, by doing the sum checks, you are basically shrink the size of the problem to be half every time. So you half it, half it, half it, half it. And every time you half it, there are half of the CPU, the half of the GPU core will be idle. So you're losing some utilization on the GPU, especially if so the number of the GPU core is somewhere around 10,000. So if you reach lower than that, basically you're wasting the GPU resources. So that's why we are like pipelining the sum checks. So the previous computation of the sum checks is become like narrower, like the size of the workload is becoming from, for example, here from 4K, sorry, from 65K becomes 32K. Then you can start in another 65K sum checks so that you can like squeeze off the computation power from the GPU. And in order to see this, the way is adding a -V option to the tool. So the way to do that is, I'm not sure whether I can close this, but yeah. So if you want to see a very verbose breakdown, you're just adding the -V. And it's randomizing something and preparing the lookup table, and boom, you have that a very detailed breakdown, like how many times it's being spent on different parts of the GKR proof. So you do some polynomial evaluation and you call the Fisher-Tropsch and you receive the challenge. And every time you will have the size of the problem. For example, here we are talking about 33 million, and then you are going to 16 million and half. And at the time that you reach lower than the number of the CUDA core, which is about 10,000 core, then you're basically start to wasting the GPU resources. So that's the time that you can inserting another run of the GKR proof, so you can keep the GPU utilization to be high across all of the time. And also we bring out the time breakdown for the Verifier too. The current Verifier implementation is very naive, so we are also working on a fast Verifier too. Yeah, again, talk is cheap. Show me the code. So everything is open source. If you're interested, just go to our repo and build it yourself and run it. If you find a bug, please please tell us. And I think we have a bug bounty program, and we will for sure reward people find a bug. Is there some approximate relationship between this halving efficiency, efficiency and the core limit? I don't understand what kind of core limit you are talking about here. So the nature of the sum checks computation is that you need to have basically you're doing something like a folding. You fold the problem. Yes, so that's related to the way that the GPU works. So the GPU has many core, like 10,000 cores, 20,000 cores. The way that the GPU works is that every single core just handle a very simple job, and that's the parallel, right? So the job that need to be done in sum checks, which is part of the GKR protocol, is that you're calculating something. You're calculating a very long array, and each of the element of that array is independent with each other. So there's no dependency, and that's a perfect perfect scenario that you can offload to GPU. But the length of the array can be longer than the number of the core that the GPU can sustain. For example, the GPU have 20K cores, but the size of the workload is, for example, 1 million. So the way that the GPU will do is that it will chunk the size of chunk the work it needs to be done into the actual hardware core. Like I process the first 20K and then the second 20K and the second 20K, so on and so forth. So there's a time, because the nature of the sum checks, you fold the workload size into half every time. So at a time, it can reach lower than 20K. And that's basically cost the other half of the, for example, if the size of the workload reached to be 10K, and then you only use 10K cores, and the other 10K is just sitting there and idle. So that's like something should be used, and then we can inserting another run of this sum checks to squeeze off the resources. And yes, I think the halving efficiency is related to the core limit, because you have to be very careful to choose the number of the job that you want to put on the GPU very carefully. It's called the number of blocks and number of threads in the context of CUDA. And by tuning that number, you basically define, like, at a time you want to offload some number of the job to the GPU. And in the case of the sum checks, that number depends on, like, especially when we are reaching to a workload size that is lower than the number of the core. And that number is very important to reaching a very high efficiency. We actually like tuning that number and exploring the number design space a little bit to find the best number. So if you check the code, I believe that number is around 256. So you need to chunk the job in a 256 chunk. That gives the GPU a higher flexibility to schedule the work and also not wasting resources. Yes. Well, I think honestly, I think the sum checks problem is just like the AI or machine learning problem. The memory access pattern is very similar, although the operation is very different. So we are basically doing all of the computation on field, not on integer or something. So it requires some cryptographic computation, not just like floating or integer. But I think the memory access pattern is very similar to machine learning problem. You have to be very careful about the number of thread and number of block. All right, it seems that I'm using too much time. Again, PCIe is something, but we are already moved to, can I minimize my head? Okay. Yeah, so at the very beginning, the PCIe is important because we do the Fisher-Shamir on CPU, but now it's on GPU. If you want to move back to the CPU to do the Fisher-Shamir, it's a hash function. It's fine. It's just taking a very the short time in here. It's 0.03 millisecond. So it's really small, and even if you move to the GPU, it won't be a significant cost in terms of time. And let me make it to be full screen. Yeah, and so this is basically the way that we accelerate the current version that we are going to release for the GKR Prover. And so the way to run that is a little bit different from the previous version. So this is like running a standalone GKR Prover. But if you want to integrate it with the rest of our toolchain, the right-hand side is the way that you can do that. So I'm going to show that too. Yeah. So still under the Expander repository, and you can see there is a script called E2E, and basically this script show all of the command that give you, starting from an application, generate the circuit, and send the circuit to the prover, all of those things. So if you attend some of our sessions in a few days ago, you will know like we have a ECC, is called the Expander Compiler Collection, and you have a way to actually generate the circuit. So basically, this is a script that we also used in our internal environment to do the CI test, to do the contiguous integration test, and it's allows you to generate the circuit, and yeah, and also you can kick off the prover. So I'm not going to show how the circuit is being generated. If you are interested, you can look the recording of previous session. But after that, you have some TXT file which actually record the circuit, and then you can use the expander, and expander can be called like this. So we having some Rust flags to tell the compiler of Rust like what kind of CPU you're using, and all you need to do is just run this command, the cargo run release, and select the GKR as the main function, and you tell them that you're going to generate the proof for KCAC circuit, and you're using some field, for example, GF2 extension 128, and you're running things in parallel of 16 thread. And that's basically give you a sense about like how fast our expander prover can be. And all you need to do, if you want to kick off the CUDA compiler, for example, all you need to do is basically just adding one line of the flag. So this basically allowing the CPU Rust prover to be able to send data to the GPU and kick off the GPU execution and send the result back. And in order to do that, still, oh, sorry, I'm not in the root. Yeah, all you need to do, oh, sorry. All right, all you need to do is just make and select CUDA and use M31 extension 3. And all you need to do is just including the path that's the CUDA library is being generated. So if you check the CUDA repository, you will be able to see there is a shared object library called Expander CUDA. And the entire implementation is just in one single file. So it's super easy to compile. And if you run this, oh, sorry. Yeah, you have to include the generated library into your environment path, and then you can kick off the entire running. So it's print out all the data, and if you go up a bit, you will also see the GPU printout, and they are binary equivalent and also much faster than the CPU version. So there are also tons of the performance statistics that you can check to making sure that you're doing the computation correctly. So this basically gives you a way to call the GPU in a very simple way. As long as your machine has the GPU, only thing you will need to do is just adding one line of the environment variable, and that's it. Then you can just use all of the toolchain we developed inside the Polyhedra, and everything will be open source. All right, I'm not seeing any other questions, so I'm going to proceed to the final part of my talk, which is our roadmap. So Expander is very exciting, and yeah, so we are currently in here. We are basically building our own ZK CUDA and a ZK PyTorch. So you can imagine all of the machine learning workloads and the AI, we are actually building proof of intelligence or proof of artificial intelligence for the Q1. And in a few months, we will release our GPU expander, and it can be also a multi-GPU expander. So we have a very cool roadmap. Many projects has been ongoing internally, and this is interactive. So we are currently building the Virgo Plus and ZK CUDA, and having the ZK PyTorch together, and then you have everything running on GPU. It's kind of like having the entire AI application, machine learning application that can be done in a ZK way, and that's what the expander can give you. And also we have a multi GPU and multi-machine expander that basically making everything super scalable, and it will happen in Q2. All right, I think that's the end of my talk today. I'm ready for any questions, and happy to answer that.
Thank you, Simon. Final questions, everybody, before we wrap up. Maybe while we're waiting, I can do a quick overview of some of the most important bits announced today. As mentioned, Monday marks the beginning of the hacking period. So during this bootcamp, you've had the chance to listen to a lot of exciting lectures for the past 2 weeks. And on Monday, we'll be beginning the hacking period, which will last for 4 weeks. And all of you will be able to build for one of the 5 bounties that were announced in the very beginning. Your projects will be able to be submitted for one of these. So there's not going to be a possibility for you to submit a project that is built from multiple of these tracks. But I mean, that would be amazing if you'll be able to do it, though, given how specific each of them are. But for best results, please pick one of the bounties and make sure to submit for it. I'm going to quickly share a link with all the different bounties that you can all engage with. You can find it in the chat at the moment. The other thing to keep in mind, we will try and provide additional workshops next week. None of them are scheduled as of right now, which is why you're not seeing anything in your calendars. But we will try and organize some impromptu workshops with the people responsible for overseeing each of the bounties, and they will be able to provide you additional details on the things you can engage with, the things you can build, and some nice ideas to keep in mind. If you're still looking for a team or haven't found the time to look for one, I'm showing another link in chat. Please make sure to navigate to that one. It is basically our board of developers. So everybody that has been looking for a team has been able to add their profile. If you haven't added your profile yet, please make sure to add that to the list as well, so that everybody browsing it will be able to find you. And in case you find someone that's interesting, make sure to reach out, say hi. There's also a dedicated team formation section on our Discord, so you'll be able to exchange words with some of the other builders of the bootcamp. So yeah, make sure to get out of your comfort zone, say hi, and make some new friends, and hopefully build together alongside with them. Right, I think no more questions, Simon. So maybe last words from you.
Okay. Happy to share. And if you find anything and check the open source release, I'm happy to build together with you.
One last request. Will you be able to please share a link to your slides in the chat for everyone? And we'll also make sure to add it to our hacker pack so that everybody that's watching the recording can have a look through these.
You mean share the slides?
Yes, if you can. If not, I'm sure you can.
I'm happy to share the slides. I will send you offline.
Perfect. Okay.
Yeah.
Right. Thank you all. This has been the final day of workshops for the week, and we'll please have and keep an eye on our announcement channel on our Discord, as we will be sharing more news for next week. Thank you all for your participation this week, and see you all soon. Thank you once again, Simon. This was great.
Thank you.
See you, everybody. Have a great weekend. Cheers.